All right. Hello, everyone. This is our third video in our sequence where we discuss state space representation. Okay. So now what we have discussed is we finished the controllable canonical form. Controllable canonical form. Sorry about that. I forgot to open up the camera, so I just did that. So we finished discussing controllable canonical form, and remember that still our task is to find a suitable state space representation given the transfer function. So we are still dealing with that part of the problem, and what we have discussed is that given a transfer function there might be infinitely many state space representations. Therefore some particular forms become prominent or important. Controllable canonical form is one of them, and in a minute after solving an example I will be deriving the observable canonical form. We don't yet fully understand why the names are as such, but later on when we will discuss some properties of controllability and observability, we will see why these forms are particularly important for us. Okay, and how they serve us in specific ways in our design problems. So before going to observable canonical form, I want to really go over an example with you. Okay, so here's an example where, again, a transfer function is given, and we are asked to compute or come up or give the controllable canonical form. Okay, there is an interesting kind of catch here. And s squared minus s plus 2. Okay. Now there is a catch with this transfer function. Otherwise it is relatively simple to put this into controllable canonical form. Can you see where is the catch? Now you see that actually the coefficient of the first or highest order of s here is not 1. Okay, so you need to be careful with that. So we will need to first take care of this detail, and then we will put this transfer function into the controllable canonical state space representation. There is another interesting thing to note here. Let me ask you, is the system stable? Now, obviously, stability relates with the characteristic equation and the roots of the characteristic equation, which is the denominator polynomial. Unfortunately, it is of third order. But still, you can immediately answer this question, and this is based on what we have learned with the Routh-Horwitz method. Okay, so you see that because there is a sign change in the coefficients of the polynomial, this system is unstable. Okay, since there is a sign change in Q of S, we can immediately conclude the system is unstable. Obviously, we can also use the Routh-Horowitz method, the Routh array, in order to come up with how many poles are on the right half plane. But we will not do that at this point. Okay, so the next thing we need to do is divide the numerator and denominator by 2. S cube need to have a coefficient of 1 in order to put this directly into controllable canonical representation. Once we do that, which gives us g of s being 1 over 2 s squared minus 1 over 2s minus 1 over 2, and we have s cube plus 1 over 2 s squared minus 1 over 2 s plus 1, and hence we have our controllable canonical representation, which are the ABC matrices as 0, 1, 0, 0, 0, 1, and I have minus 1, plus 1 over 2, and minus 1 over 2 as coefficients coming from the denominator polynomial. And also we have b given by 0, 0, 1, and c given by the coefficients of the numerator polynomial, right? We have minus 1 over 2, minus 1 over 2, and 1 over 2. Okay, so that is our controllable canonical representation. Okay, so I haven't put the question at the top, but the question was to find the controllable canonical representation for the given transfer function. Now let us check back the transfer function, okay, just to in a way exercise. Okay, check back the transfer function. We should arrive at the same transfer function that we started with. Okay, so remember what is the transfer function? Will be g of s will be c times si minus a inverse b. Okay. So let us take a look first at Si minus A. That is equal to S minus 1, 0, 0, S minus 1, and I have 1, minus 1 over 2, and S plus 1 over 2. Now, first I want to also find the determinant of this matrix, because I know that this is equal to 1 over the determinant of Si minus A times C times the adjoint of Si minus A times B. Okay, so I will need to find the determinant of Si minus A, and in order to do that, what I will do is I will basically conduct elementary column operations. Okay, so that means using Gauss-Jordan elimination. remember, if I can make this matrix upper or lower diagonal or triangular, that means if I have zeros in the below the diagonal entries, the determinant is determined by just multiplying the diagonal entries. Okay, so if I multiply the first column by 1 over s, multiply by 1 over s, and add to the second column, this will be 1, and added to minus 1, it's going to give me a column of 0. So the first column is the same. The second column becomes 1 and minus 1. I have 0 here. S remains over here. And 1 over s times 1 becomes 1 over s. So this becomes 1 over s minus 1 over 2. Okay? And we have the same column as our last column over here, s plus 1 over 2. Okay? So now I also would like to make I want to basically make this upper triangle over here as 0. Okay, so that I can multiply the diagonal entries to get the determinant of this matrix. So what I'm going to do is I will do the same thing here. I will multiply this column by 1 over s, and add to, again, multiply by 1 over s, and add to the next column. So in this case, what I will have is s0, 1, 0, s 1 over s minus 1 over 2 over here. And when I add this to the next column, what I will have is 0 here, 0 here, and a bit more sophisticated entry here. So I will have s plus 1 over 2 plus 1 over s squared minus 2s minus 1 over 2s. Okay, so that becomes my matrix. Okay, now this looks complicated, but what I need to say is that the determinant of this matrix, because of this upper triangle over here, all zeros, basically determinant si minus a is given by product of all diagonal entries, because the upper triangle is all zeros. Okay, so what I will have is that this is going to be equal to s times everything that is over here, s plus 1 over 2 plus 1 over s squared minus 1 over 2s. So I'm going to multiply all of this by s squared. Okay. So what is this? This is going to be s squared times s. So I'm going to have s cubed 1 over 2 times s squared. I will have 1 over 2 times s squared plus, or let me start with the minus here, minus 1 over 2s. So minus 1 over 2s times s squared. So I will have minus 1 over 2s. And finally, I will have plus 1 as the determinant. Okay? And remember that this determinant is supposed to be equal to the characteristic equation. This needs to verify the denominator polynomial of our original transfer function. Let us check. In our transfer function, we had 1 over 2, minus 1 over 2, and 1 as our coefficients. 1 over 2, minus 1 over 2, and 1. Okay, so characteristic equation is verified. And this is at the denominator of the transfer function. Let us also calculate g of s. G of s is c times, so it is 1 over q of s, which is the determinant that we have just calculated, times c, which is given by minus 1 over 2 minus 1 over 2, 1 over 2, times the adjoint of the Si minus A matrix. So I'm going to leave it to you to verify this. Okay, but the adjoint matrix will be S plus 1 over 2 minus 1 over 2 minus 1 minus S plus 1 over 2 S times S plus 1 over 2 1 over 2S minus 1 S square sorry, this it should be S, and we have also the B matrix here, 0 0 and 1. Okay, so you see that this last multiplication, it's easier to do this last multiplication first because of these 0 entries here. Only the last column actually becomes involved. Okay, so 0 times this term, 0 times this other term, and 1 times 1. So this becomes just 1. And then we have S and we have S squared as a result of this multiplication. So we have a row vector multiplied by a row matrix multiplied by a column matrix. So we will have 1 over Q of S, and it's going to be these coefficients multiplying these terms. So it's going to be minus 1 over 2 minus 1 over 2 S, sorry, yes, minus 1 over 2S and plus 1 over 2 S squared. So in that case, the numerator polynomial becomes 1 over 2 S squared minus 1 over 2S plus 1 over 2, sorry, minus 1 over 2, sorry about that, minus 1 over 2 minus 1 over 2. So divided by the denominator polynomial Q of S, which we have already verified, right? This is going to be S cube plus, sorry, 1 over 2 S squared, 1 over 2 S squared minus 1 over 2S minus 1 over 2S, and finally plus 1. And let's check also the numerator. The coefficients are 1 over 2 minus 1 over 2 minus 1 over 2, 1 over 2 minus 1 over 2, and minus 1 over 2. Did we make a mistake somewhere? No, okay. So this is also verified. Okay. All right, so let us now move on to how we can derive the observable canonical form. In fact, this is maybe the most kind of tricky state definition, requires the most tricky state definition. It's going to be, in a way, some kind of a recursive state definition. So let us start with an example. Okay, start with n is equal to 3 as an example. It's going to be easier to see it on the example, and then later on we will generalize it to the general n. Okay, so remember that our transfer function g of s, which is equal to y of s over u of s by definition, in this case is given by b1s squared plus b2s plus b3 for the case where we have n is equal to 3, and in the denominator we have simply s cube plus a1s squared plus a2s and plus a3. So this is the n is equal to 3 case. Now what we will do is that we will cross multiply the terms. Okay, so we will have s cube y of s plus a1 s squared y of s plus a2 s y of s and plus a3 y of s, that is equal to b1 s squared u of s plus b2s u of s plus b3 u of s after cross multiplication of the terms. Okay, now let us divide everything by s cube. So let's divide everything by s cube. That will leave us with y of s plus a1 s squared over s cube. So I have 1 over s y of s plus a2 1 over s squared y of s plus a3 1 over s cube y of s, and that is equal to b1 1 over s u of s plus b2 1 over s squared u of s, and finally b3 1 over s cube u of s. Now what I will try to do is to first leave y of s on the left hand side. Okay, leave y of s on the left and rewrite y of s recursively, and I will illustrate as, okay, so you will see what I mean by that. Okay, so I will try to write y of s, but I will try to multiply 1 over s's one by one. So what I will do is that I will put a 1 over s here, and then I will put all the terms with a single 1 over s inside. Okay, so we have, for example, over here this term. So that's going to come with a minus sign, minus a1. 1 over s is in front of the parentheses. So minus 1 over s, minus a1 y of s. And also I have another term coming from here. Okay, so that's going to also come here, plus b1. Again, 1 over s is in front of the parentheses, u of s. Now we have terms with a term 1 over s squared. So what I will do is I will add another 1 over s term and open another parenthesis, and now write all the terms with 1 over s squared term in front. Okay, so that's going to continue like a2 y over s y of s plus b2 u of s, and I'm going to repeat this one more time where I will write down every term with 1 over s cube term, and that's going to be minus a3 y of s plus b3 u of s. First parenthesis, second parenthesis, third parenthesis, right? So let me see whether I have one more. Okay, So I have u of s, close parenthesis here, close another parenthesis. Okay, close another parenthesis here. That completes our expression. So we have expressed y of s. So what I will do is I will recursively define the states. Define the states. So let me not write here because I'm gonna make this definition. Let me change a color here. So what I will do is that this I will define as my first state. So this is gonna be x1 of s. This whole thing will be my x2 of s. And finally, the entire expression will be equal to x3 of s. Okay? So let's pause a minute and think about how this looks. First of all, the interesting thing is that this puts essentially interesting relationship between the states, and also it also at least tells us that the output equation becomes very simple because it's simply equal to the third state. Okay. Now we have y of s equals x3 of s. That gives us the output equation, but also tells us that we can put x3 of s wherever we see y of s. So let me try to write down the first state equation. So I have x1 of s over here given by 1 over s times minus a3 y of s plus b3 u of s. So that means that s times x1 of s is simply equal to minus a3. Instead of y of s, I can write x3 of s plus b3 u of s. Now think about what s times x1 of s is. If I go back to time, I will have x1 of t derivative here, and that gives me minus a3 times x3 of t plus b3 u of t. Now this is an expression for x1 derivative in terms of all the other states and the other inputs. So this gives me my first state equation, right? First state equation. Let me do the same with x2. So similarly, I have simply s times x2 of s. Remember what here was. x2 of s was equal to this expression over here, right? So what I'm gonna get is that this is equal to so s times x2 of s is equal to minus a2 y of s plus b2 u of s plus x1 of s, because x1 of s is simply the last term in that expression. So again, y of s is our x3 of s. So what I have here as my state equation is that x2 dot of t is equal to minus a2 x3 of t plus b u of t plus x1 of t. Again, an expression entirely in agreement with what a state equation should look like. Okay, so this is our second state equation. And similarly, we can also derive x3 dot of t as minus a1 x3 of t plus b1 u of t plus x2 of t as our final state equation. So now let's put these in our matrix form. Okay, put into matrix form. Obviously, you will have to rearrange the coefficients so that you have coefficient of x1 first, coefficient of x2 first, etc. But here we have x1 dot, x2 dot, x3 dot, the derivative of the states. That is equal to a 3 by 3 matrix times the states themselves, x1, x2, and x3, plus a column matrix times u of t. And let me try to fill in this. So x1 dot of t is equal to no x1 term, no x2 term. So I will have 0, 0 here, and minus a3 as the factor of x3, and also b3 times u of t. Similarly, from the second equation, x1 term, there is one x1 term, there is no x2 terms, but there is a factor of x3, which is minus a2. And also we have, by the way, this should be b2 over here. So b2 u of t. And finally, from the final equation, I have no x1 term, there is x2 term, and then minus a1 as the factor of the third state, and then b1 as the coefficient of the input. Okay. And also, what is the output equation? Output equation is equal to a row matrix times the states. We know that the output is equal to the third state, so I just need to multiply that by 1 in order to get these matrices. Okay, so this is known as the observable canonical form. Okay, and we have done this for n is equal to 3 case, so I will just generalize it in a minute, but you can see how the coefficients of the numerator and denominator polynomials are actually reflected in this expression, and there is an interesting symmetry between this representation and the controllable canonical representation. If you look at both of them, you will notice the similarity. In fact, all of these matrices looks like A matrix is transposed, B matrix has become the C matrix transposed, and the C matrix has become the B matrix transposed. Okay, note the transpose symmetry between the controllable and observable canonical forms. Okay. So for a general case, I will write this for completeness. It is fairly straightforward to generalize this from the example that we have done. But in this case, g of s, we assume that it is given by a proper transfer function where the numerator is 1 degree less than the denominator. It starts with b1, goes up to Bn, and the denominator starts with s to the power n with a coefficient of 1, and then comes the coefficients different from 1, s to the power n minus 1 up to an. Okay, so we will do the same, right? We will cross multiply the terms because this is equal to y of s over u of s. Okay, so y of s can be recursively written as, in this case obviously we have a series up to n, so it's gonna be equal to y of s plus s to the power n times y of s plus a1 s to the n minus 1 y of s plus an y of s, and that is equal to b1 s to the n minus 1 u of s up to bn u of s. And taking all of these terms to the right half, okay, divide by s to the power n, divide by s to the power n, isolate y of s on the left hand side. So y of s will be recursively written as, again, 1 over s times all the terms with only 1 over s, a1 y of s plus b1 u of s plus another 1 of s times minus a2 y of s plus b2 u of s plus 1 over s, and this goes on like this, okay? And then, right? So again, this becomes simply x to the power n minus 2 of s. This becomes x to the power n minus 1 of s. And finally, this whole expression becomes x to the power, sorry, what I am saying, not the power, I'm sorry. I just kind of lost what I am saying. So this is xn minus 2 of s, this is xn minus 1 of s, and this is xn of s. Okay. So the general matrix form is simply the generalization A observable canonical form is equal to 0, 1, 0, all zeros, 0, 0, 1, all zeros up to here. You have 0, 0, 0, just the 1 in the last entry, and then minus an minus 1 minus an minus 2 up to minus a1. B observable canonical form is just the numerator coefficients bn minus 1 up to b1. And CO is equal to 0, 0, 0, and 1. Let me also remind you the controllable canonical form to see the symmetry here. So a controllable canonical form looks like this. You just transpose this matrix 0, 1, 0, all zeros, 0, 0, 1, 0, all zeros, Then you have, let me erase this part and just have some more. We have 0, 0, 0, all 0, 0, 1, and we have minus an minus 1 up to minus a1. Okay, minus a2 here. You see that this matrix actually here is like transpose. So B, on the other hand, B controllable canonical form is just coming from here, right? 0, 0, all 0, 0, and 1. And C controllable canonical form is simply the B coefficients, Bn minus 1, B1. Okay, so you see that there is a very stark symmetry between these canonical forms. Okay. Let me catch my breath for a minute. All right, so we have seen how we can go from the transfer function. Okay, so we have seen how to go from state space to transfer function. That is a unique relationship, unique solution. We have also seen how to go from transfer function to steady state space. Not unique, but we have so-called canonical forms. Canonical forms with some properties. In fact, it would be useful to learn the actual forms by heart, so that given a transfer function, you can immediately put it into this form by simply projecting the coefficients to their respective locations. But you might also wish to remember how those states were defined, but you don't need to, rederive it every time that you need it. Essentially, okay, but it's still interesting way the states have been designed in order to arrive at these particular canonical forms. Okay, so what we will study next is certain properties of state space representations and of some of the canonical forms. Okay, canonical forms, and later we will see how to exploit these properties. Okay, in fact, the first thing that I'm going to discuss in the next video is the concept of controllability. Controllability and complete controllability of a state space representation. Now, it is important that this will be a property of the state space representation, because there are infinitely many state space representations. So this means this property is not a property of the system, but it's a property of the chosen state space representation. Okay. Also, we will continue with observability property and complete observability. we will see that these properties may be necessary in order for us to be able to use the state space representation for further design purposes, such as for designing a controller for it. Okay, so that's going to be all for this video. Thanks for your attention for this about 45 minutes. So see you in the next video.